Hey everyone, my name is Caleb Shepard, and I'm here to present to you cryptographic security in a post-quantum world. There are several advantages of quantum computing. One of them is called superposition, and these really have to do with the behavior of subatomic particles. It's something that we use to our advantage when working with quantum computing. There's the concept of a qubit, which holds more information than a 0 or a 1, which is in traditional computing referred to as binary. So qubits not only hold more information, but superposition allows their particles to be in multiple states at the same time. We have this idea of the Heisenberg uncertainty principle, which states that the exact position and momentum of an electron cannot be determined at the same time. The reason for that is because when we observe an electron, we alter its state. The smallest thing we have to observe other electrons with is electrons. So when you shoot an electron at another electron, you either know how fast it was going or you know where its position was, but it's really impossible to determine both. Multiple qubits can be imposed together to perform massive calculations using superposition. The second idea we have is called entanglement. It's the idea that two members of a qubit pair exist in one quantum state. Einstein described entanglement as spooky interaction at a distance. We have no idea how it works, but we know that changing the state of one particle will change the state of the other particle it's entangled with in a predictable way, which happens even when they're separated by very long distances. So adding extra qubits to a quantum computer doesn't just increase its computing power linearly, it increases it exponentially. We're using the idea that these particles interact with each other over long distances in predictable ways, containing qubits, which gives us exponential scalability when we add additional qubits. And instead of using a processor or using some sort of circuit to determine how bits should be smashed together, the qubits have already determined how their outputs or how their states are going to be affected by one another in a natural way, which is very interesting. So the third thing I want to talk about is called decoherence. This really is a disadvantage of quantum computing. And we know that qubits interact with their environment, which eventually decays their states. So much of the research we're doing right now is being done in quantum computing is in minimizing the effects of outside environments on the qubits inside the machines. You'll see a lot of these machines operating at super cooled temperatures inside of a vacuum, but the qubits inside of these machines will always ultimately decay, and that leads to a non-deterministic output many times. I didn't know about this when I was making this presentation, but there's a lot of talk about something called quantum supremacy. So the quantum advantage we have, especially in cracking algorithms like RSA that rely heavily on factoring large prime numbers, is that quantum computing has a strength of exponential scalability as you add more qubits. But because the states are so difficult to maintain and they're non-deterministic, there hasn't been a clear advantage or a clear winner between quantum computing and traditional computing. But we see significant speed increases in solving certain cryptographic puzzles. So we know that quantum computing is very good at cracking a lot of cryptographic standards that exist today. So we're really looking for that proof that quantum computing is objectively better than traditional computing. And when we find that proof and when we're able to determine that, we'll move to a period called quantum supremacy. So I alluded to this earlier, but quantum computers are great at factoring. We have the advantage of coupling and entanglement, which we don't really understand, but it allows us to take problems that usually require non-polynomial or near non-polynomial time in practice and just turn them into decomposed keys like it was nothing. While I was making this presentation, I found a lot of evidence that quantum computing really was superior in cracking a lot of cryptographic standards, but I really wanted to condense this down so that way I could communicate this idea to everyone. So let's take a moment to talk about Shor's algorithm. It's a very important algorithm here. Shor's algorithm is an algorithm that quantum computers can use to factor or crack RSA, and they only need one modification called the quantum period finding subroutine. And it involves very complicated, extensive higher order math, but we have to keep in mind that this exponentially scales in effectiveness with additional qubits, which allows us to crack things like RSA in polynomial time. So let's talk about some of the advantages that Shor's algorithm has. It's been used to solve certain cryptographic puzzles that have been found to be compatible with the qubit coupling advantage that quantum computers had. And there's an ineffectiveness of traditional computers in factoring large prime numbers, and that's the line of defense we rely on in things like RSA, DSA, and ECDSA. It's just that we use these large prime numbers to generate our public and private keys. So that is the backbone of a lot of these encryption standards, and it's what quantum computing excels at breaking. IBM was able to prove effectiveness in a theoretical quantum computer back in 2001 by using Shor's algorithm to factor 15 into 3 and 5, which is very simple, but they were able to show that you could use this quantum period finding algorithm and really ramp up its effectiveness. RSA is a very popular standard, but you can crack it by factoring a public key with size n. This is very difficult to say, as I said earlier, but you want to find a number besides 1 and itself that factors or decomposes this key. And classically, factoring n will become increasingly time-consuming. The classical time complexity to break RSA using the general number field sieve, and there are a lot of sieves out there, and some of them are more effective or less effective than others. But I wanted to put this into perspective for you. The big O time is non-polynomial and exponential. So what's the time complexity with a quantum computer? It's somewhere between big OB and big OB squared. It's normally going to land approximately between B and B log B. It was difficult for me to come up with an exact answer, but in almost every case, it's going to be very, very close to B. This is something that's dependent on the number of qubits in the quantum machine and dependent on a lot of physical factors. So this is a proof of the efficacy of quantum factoring using Shor's algorithm. And if you want to see the full proof, you can find it on Wikipedia. It's several pages long. It involves very complicated higher order math. But if you really are curious, I would recommend that you check it out, because you could look for yourself and try to figure out different scenarios where quantum computing would beat traditional computing in cracking these things, and you could really see how effective quantum computing could be. So I talked about Shor's algorithm, and to satisfy your curiosity a little bit, I wanted to provide a high-level overview. So the first assumption we have is that n is odd, which means it's not divisible by 2, and that's going to be the case because we don't want to have easily factorable keys. And the second assumption is we have a random number less than n that is chosen. So the first step we use with these two numbers is we take the greatest common denominator found using the Euclidean algorithm, and if it's non-trivial, you found your key. Otherwise, we're going to use the quantum period finding subroutine, which finds the period of fx ax mod n, and this is really the key to factoring large numbers with quantum computers. In this example, is we are able to use the quantum period finding subroutine in a way that makes this non-polynomial. And I'm not going to post the math here, but again, if you're really curious, I really do recommend that you check this out for yourself. So if r is odd, we're going to go to step 1. If a r2 equals -1 mod n, we also go to step 1. And at the end, we're going to find that the non-trivial factor of n is actually one of these two things, GCD A. I'm not going to read that, but we're able to find this almost like a binary search, which is pretty insane. So what does all of this mean? Well, we know that the quantum period subroutine is kind of complicated. I'm not going to talk about it, but it's really the thing that unlocks a lot of potential for quantum computing. We also know that traditional secret key cryptography involves public and private keys, but those rely on large number factoring, right? So decoupling is an obstacle to quantum computing and to developing the machines physically. So if you want to keep your data safe, I'm just going to summarize it in a, a little bit of an oversimplification, but you could use something like AES 512, and we're not very confident that quantum computing would be able to crack that in a reasonable amount of time. And another thing you could do is try to use encryption standards that require non-polynomial time. You really have to do the math for yourself on a lot of these things because there is a predictable and logical way to determine whether or not something is safe. And I'm not able to go through all of those things in this presentation, but keep in mind you still have things like one-time pad encryption. It's theoretically secure, and if it's theoretically secure, it doesn't matter how much computing power you have, you just really won't be able to crack it. Two easy takeaways is that more qubits is equal to exponential cracking power, and you should use AES 512. Thank you, everyone. I hope that this helped you understand quantum computing and that you'll have a better grasp on how encryption standards should be changed or should be used going on into the future. Thanks again.